Today we're going to show the Maxon motor with encoder for position control using the incremental encoder and Halls for commutation. Previously this Maxon motor just had Halls and motor power, but there's an option for incremental encoder. You can see that this was a single-ended encoder because we didn't get the differential encoder option, so we had to get a single-ended to differential converter. This is a US digital cable converter, and that takes a single-ended and converts that to differential. I put my own twists in these wires. It would be good to button them up. Shield's always nice, but at least some clamps to keep the wires together. So of course we have Halls and motor power wired to the feedback connector. Now we have Halls incremental encoder +5 and ground. The data sheet calls out some tools for doing the crimping on the Samtech connectors. This is a real fancy tool and maybe has a lead time. This is a low-cost Sargent tool that I use for doing my own crimping in the lab. For production, you want to use something like this because it's really designed specifically for the Samtech connectors. But if you're just in the lab making a quick connect, you can go ahead and do that. Today it's Maxon 24 volt. This could be like a 48 volt or a 75 volt power. That'd be fine. And I have a serial cable kit. It's ACJ. That's a small ACJ drive. Needs a serial connector that has this Samtech type connection. So I'm using the B&B USB to serial adapter here for that. So previously we were showing the ACJ with the Maxon Halls and motor power only. That's for velocity mode. Not very good for position control. So today we're going to see how to hook up the feedback device to the ACJ. I'm going to use a +5 volt out for Halls and incremental encoder. The incremental encoder is a US digital. You know, it's got lines, 500 lines times 4, 2,000 counts, and it's single-ended. If we take a look at the data sheet for this, we can see the pinout here. But notice they also make a differential feedback device. These guys at US Digital may even have some absolute stuff, but it may be kind of big. But I think for this package size, a differential is pretty good. So that's my recommendation. Anyways, we got the single-ended here. Oh well. Let's figure out how we're going to adapt to it. So they have some cables, cable adapters. So there's a cable that goes from the feedback device to the converter. So it looks kind of like this, EADL10 with the single-ended here and differential out, connecting to a cable connector. So here's the pinout color for the differential, and the pinout color for the single-ended is also listed in here somewhere there. So single-ended, you got the wire colors here. So previously we were doing Maxon Hall velocity, and we can see there's a little bounce at the end of the move. It's not very stiff. You know, I can turn the shaft and, you know, it kind of comes back a little bit. So what we're going to do today is switch over to using the encoder. So on the basic setup screen, brushless rotary, yeah. Now I've got a primary incremental connected. I can change to position mode. Yeah, software program's fine. Sinusoidal commutation, we're no longer doing estimated sinusoidal. And the multi-mode port on the drive can buffer the incremental out. That's good. CME2 wants us to confirm the feedback. That's a good idea. So feedback, 500 lines, 2,000 counts, same data. We're going to do some tuning here. We'll just say OK to this. We could calculate, but I'm just going to go through and tune it. The bandwidth hasn't changed because that's based on the inductance and resistance of the motor. The velocity loop's definitely going to change. I'm going to knock some numbers off of this because it might be a little high. Maybe we should calculate. Yeah, let's just calculate. So, well, I have to go through the tuning anyway, so why not? So yeah, the gains for VP and VI much lower. There's a velocity limit set there. That's fine. I'm okay with that. P loop, standard gains. Okay, before we do the scope for tuning, let's check out the phasing. So tools, manual phase, enable, forward. Okay, as I rotate the current forward, I see the counts going negative. That's wrong. So invert that. Otherwise, we'll get positive feedback or negative. Yeah, positive feedback. So, okay, going forward, counts go up. That's good. Commutation is the same. No change there. So you've got a Hall offset, invert the motor for the direction we want, positive, and then phase the thing. So that's good. Now we should be able to do the tuning of the loops. We'll do a quick check out of the current loop just because we can. So no change there. Current loop looks good. So velocity loop. Let's look at channel 3 current actual with the velocity. And if our gains are too high, you'll get a little too much buzzing there. So set it back down to 500. There's a little ring there. We can knock that down a little bit if you want to attack that. Got a little overshoot there. We're going to check out the integral here. If the integral is too high, we may see severe integral windup. Yeah, there's integral windup with some tilt. So maybe we don't need so much integral to hold steady state. That looks pretty good, so we'll stick with that. So that's velocity loop tuning. Don't forget to save the flash, but we'll do a profile move here to get things started. So 2000 count should be 1 rev. There it goes, 1 rev. And this should be 10 revs, channel 3, current actual. Yeah, so that's 10 revs, and there's good stiffness on that motor with the encoder now. My integral's a little high, I got a little wind up there after the move, so I'm going to knock that down again. So the control with encoder is really good for holding position and making position moves. So this is the way to do slow speed and good stiffness here. We could try a little bit more gain. Little buzzy on the encoder, but that's good. The following air is coming way down, and stiffness here is pretty good. So just going to do a quick check on some other limits while we have time. So we'll look at the voltage bus, the voltage terminal servo. This is the D and the Q summing up, so that's an idea of the bus, a voltage out, but not all of it. There's still the imaginary part. Miscellaneous, well, status warning, voltage limited, and we can try some faster speeds here. Let's see if we can do 10 revs, 5,000 RPM. Let's go double the distance and see if we can hit 10,000 RPM. Oh, velocity limit, gotta fix that. It's on the V-loop screen. Always make this 10% higher than what you want to go at least. It's telling me I can't do that because of the bus voltage, but that's okay. We'll see what happens if we try to go faster than we can. So, all right, we seem to be doing it. The IR drop's not too big, and I'm not hitting the voltage limit yet. Oh, didn't try 10,000. So, yeah, the bus voltage is about half of the servo voltage. Yeah. There we go. I tried to go fast. So here we have the voltage. Terminal servo is approaching the bus voltage in orange. We do not see a limit yet. Give it a little further distance so I can actually hit that or try to hit that 10,000. Okay, so there's a little bit of error build up here, voltage limit warning, just at the end of Excel while we're running a little bit, but then the error comes down, the following error in blue comes back down, so it's not, this is not there's not a lot of margin in this speed here, so I'd slow it down a little bit. And you can see a little regen occur during the decel there, but that's fine. Let's try to do something we can't do for trajectory. Let's add another 200 RPM on that. Okay. So again, this is bigger than what we want to do. The warning about the voltage and IR drop is there. But let's see if we can do a little bit faster. Yeah, I know. Okay, 20%. Yeah, so again, the following error starts to grow when voltage limited, but it comes back down. All right. Start at the beginning here. All right, so I'm just going to say it's a 20,000 RPM motor, even though it says it's 15,000. No, do not calculate. Okay, let's put in 20,000 there. It's crazy fast, but trying to get to the limit here with the bus voltage. So following error. There we go. So as you can see, we started becoming voltage limited around less than 15,000. The error was constant, the following error grew, and then we got a following error fault. So on the control panel, we can clear the following error. Let's go back down to something more reasonable. Maybe we'll bump into it here. No, still an error. So yeah, if you want to go this fast, you're going to need a 48 volt supply, not a 24 volt supply. So clear fault. So there's a little bit of margin in the system here. A warning's okay, but be careful. If that thing is constantly voltage limited while you're running at speed, you've run out of voltage. And you can see here that the terminal voltage servo is approaching the bus voltage. So the terminal voltage servo right there. There is an option on the iLoop screen for max speed. That's what we got here. It's not going to be as smooth at that speed, but we got some inertia to carry us through it. So give it a little jog, forward, reverse. This thing will go, real slow. Good position control or slow velocity control. That's not a lot of counts per rev, but that's sufficient. And then save to flash. You don't want to lose all your hard work tuning the thing. Just get a power cycle and start all over again. And then if you want, save a CCX file. So there you go. That's it for today. Thanks for watching Maxon with an incremental encoder and Halls in position mode.